Hello, my name is Matthew Wilson, and this is our intro to negators and decoders. So, what is the process of negating? And the definition is a statement that has the opposite truth value of that statement. So, some examples of this can be seen as negating the number 19, which would simply just be negative 19, or in binary, if you were to negate 0001, 1010, the answer depends on its form. So in one's complement, which you just complement each bit, so it would turn into 1110, 0101, and then two's complement is just adding 1 to the one's complement. So your answer would be 1110, 0110. Next question is, what is a decoder? And a decoder is a combinational circuit that accepts a binary input and produces an output in some other form. So today in our lesson, we have built a 3x8 decoder in active low inputs. And the 3x8 just comes from having 3 inputs and then returning out 8 outputs. And this can be done for multiple as 2x4, 4x16, and so on. And then the active low and active high outputs and inputs can be differentiated by truth tables or through AND or NAND gates, which I'll get into a bit later. But for the truth tables, you can see here on this next slide that active high outputs and inputs, can be represented as all of the positive values being ones and the rest being zeros, versus active low inputs, which is the complete opposite, where all of the ones now turn into zeros and the zeros turn into ones. And now I'll go ahead and show you guys in Logisim how to put this to the program. So here in Logisim, the first thing I'm going to show you guys today is a neat little shortcut in order to kind of introduce you how to bring in a previously made circuit. And you can simply do that by going up here to your bar, clicking Project, Load Library, and then go into Logisim Evolution Library here. And once you open that up, you can go ahead and open any of your original projects. So as you can see here, I went ahead and added my C3 for the given assignment today. And what that does is I can just pretty much go ahead and open that and take out whatever I need to take out, which is really useful, especially in this case here, seeing as we had to make use of this adder 4 in order to create our increment wrapper here. Our first task here was to create a negate 4 circuit. And basically what this does is going to perform the ones complement operation and then add 1. So basically just our 2's complement form. But instead we used our exclusive OR gates as well as have an increment option of 1, which I'll go ahead and test now for you guys. So as you can see here in our test circuit, I already have an example thrown up here. But basically, to simplify it, if I went ahead and entered in any number here, let's go ahead and say, for example, we'll enter the decimal 5. Go ahead and turn this increment off. As you can see, our input was 5 and our output was 5. But if we go ahead and use the increment, which is going to add the 1, or in other terms, start the 2's complement form, it's going to go ahead and turn that into -5, which is going to negate that number, which is exactly what we're looking for in this process. Going back to inside the circuit, we can see that we made use of our exclusive ORs, as I had mentioned earlier. And basically the reason we use these exclusive OR gates, because you're able to control whether or not the complement occurs. So right here is considered like our increment number. And so whenever we turn this on, it's going to make all of these values 1, which will go ahead and perform that 2's complement operation, as you can see here in our test. Same logic applies. When you turn it off, it doesn't negate it, but when you turn it on, it does. It provides that 2's complement operation and turns that into a negative number, or in reverse, if I did -5, it would turn into +5 as well. And then for this example, we like I said earlier as well, we used our adder circuit. And so loading that in, I think that was the most efficient way to add that increment of 1, just because it was a previous assignment and we'd already done something similar, and all we had to do was just get rid of our B values and just keep our A values, which made it much simpler just to easily add that 1 value and pass it through everything that we need to do. For our next task, we have our decoder. And at first, this can kind of seem intimidating, but it's actually quite simple to understand. As you can see, we still have our 3 inputs here, X, Y, and Z, with our 8 outputs here, Q0 all the way to Q7. And these output numbers, why these are all 1 and this one's 0, is because of our active low inputs that we have. As I described previously in the truth tables, that when your input is going to be 0, the remaining numbers are going to be the ones, as you can see here. Our inputs are 0, and then the rest is ones, and then Q0 is 0. And then down here is called our enable input, which I've added to just basically, whenever this turns on, by using our poke tool here, whenever this turns on, it's going to turn all of our inputs to 1, no matter what it is. As you can see, it turned that 0 into 1. And I can go ahead and make this inputs whatever I want, but it does not matter. This enable input is on, so all outputs will be 1. And then to go ahead and test this circuit, same thing here. So right now we have the binary input of 6, which in return should give us our Q6, which is going to be 0, 1, 2, 3, 4, 5, 6 on 0, and the remaining numbers being ones from our low input outputs. And then if we went ahead here and tested our enable button as we did previously, you can see that it turns all of our inputs and outputs, or sorry, all of our outputs to just 1. And this can be seen with any number. So we put in 5 here. You can see that Q1 or Q0, Q1, Q2, Q3, Q4, and Q5. Q5 is at 0, and the remaining numbers are 1. And if we go ahead and flip on that enable switch, all outputs will be 1. So kind of coming full circle here, as I again stated previously, this can be used for a larger number of inputs and outputs, pretty much just by doing the same exact process, except doubling it. So if we had a 2x4, we'd actually be going down, so we'd be only having 2 inputs and 4 of these outputs. And then vice versa, we could have a 4x16, so adding 1 extra input here will give us another 8 outputs. And then also I said that you can tell the difference between active low and active high inputs based on AND or NAND gates. So as you can tell by our question or our equation, we needed low inputs and outputs, but if we wanted active high inputs and outputs, we would go ahead and actually make these NAND gates into AND gates, which will make the rest of these remaining ones into zeros. And we'll make our Q0 here, or whatever our input is, into a 1, as shown in the truth table as well. Decoders can be useful for many things, but primarily for peripherals and CPUs inside your own computer. So basically, when your CPU, your central processing unit, needs to communicate with a peripheral like your keyboard, a hard drive, anything like that, it's going to get a code sent through it. And it's going to be put through a decoder in order to speak with that device only. And that is all I have for you guys. Thank you.